Please subscribe, like, comment and share to get more videos like this that are so much educative and practical. May God bless you. Shalom. See you in the next video. Okay, so we are having a sample scenario before us, and it is telling us that during the physics lesson, the teacher tasked learners to release two stones of different masses from the same height. They were surprised that the stones hit the ground at the same time, and this troubled them since the stones had different masses and volumes. The teacher told them that all objects fall freely at a rate between 8.5 meters per second squared and 11.5 meters per second squared. And this troubled them the more. Task helped the learners settle their confusion. Now, as a physics learner, what are you going to do here? Now, your decision on what you're going to do depends on the availability of the materials you've been set before, or like the materials you've been given are the ones that are going to guide you on which practical you're going to do under this. But literally, it is testing experiment. It is testing acceleration due to gravity. So you're going to move on, and now we are going to begin with the hypothesis. We are going to begin by getting the aim. We get the hypothesis until we move on with our practical. So if we go to the aim, what aim are you going to do? Our aim will be, of course, targeting an experiment to obtain the value of acceleration due to gravity. And as we can look through, it is given to us that an experiment to determine acceleration due to gravity, G, so as to settle the learners' confusion about the teacher who told them that all objects fall freely at a rate. So you realize we are connecting the aim to the purpose, as in our aim is to get the acceleration. Then after getting it, of what use is it? We are going to use it particularly to advise the learners who are confused. So you join the purpose to the aim, and that's how you get a concrete aim for your experiment. We move on to the hypothesis. The hypothesis, it is acceleration due to gravity is between 8.5 meters per second squared and 11.5 meters per second squared. Why are we predicting that the acceleration due to gravity is between these values? We are predicting so as to settle the learner's confusion about the teacher who told them that all the objects fall freely at that rate. Always be mindful to join the purpose, the hypothesis, and to join the purpose to the aim. We have the variables. We have independent, dependent, and constant. As you can look at them, under independent, there is length of the pendulum, L, meaning you're going to use the symbol L. And then dependent, you are having time t for 20 oscillations, and then the period of oscillation, that is denoted by capital T. Please be in place to always differentiate between the two. Time t, it is in small letter, and then period of oscillation is in capital letter. Don't mix them. Then we go on to control variables. We have the starting position of the oscillations, angle of displacement, and also mass of the pendulum. Yeah, it can really affect our results. So in this case, we've made it to be constant, so it is under control. And so on materials, there we have them, as you can see. Then move on to another thing, and that will be the experimental setup. I will always emphasize experimental setup. Make sure it is a working, talking diagram. Working, it means that it is very well drawn and very well labeled. If you draw a diagram which is not labeled, you miss out a point. So always endeavor to put that into consideration. Okay, we shall not stay on that. Move on to another thing, and that will be the steps. Steps number 1, you're saying you first set up the apparatus, or if I may read through, as you are following, the apparatus arranged as shown in the figure above. The thread was adjusted to a length beginning with L equals to 20 centimeters from the center of the bob to the point of suspension. Okay, the bob was displaced through a small angle to the side and allowed to oscillate for 20 oscillations, as we shall look in the video of how those 20 oscillations were measured. The time T for 20 oscillations was measured with a stopwatch. You can use a stopwatch or a stop clock, but in this video we used a stopwatch. So hoping that you know how to also use the stop clock if at all it is the one in place. Moving on, the period T of 20 oscillations was calculated from that formula. T equals to small t, which is the time of oscillation, divided by the number of oscillations, which are 20. After getting that, you record it somewhere, then procedure F. We are repeating the other upper procedures up to somewhere. We are repeating procedure B to E. Why are we repeating? We're repeating them for the length of 30, 40, 50, 60, up to 70 centimeters. When you convert this into meters, you'll be getting 0.3 and up to 0.7 meters. So take note of that, as we shall look in the table the way we converted them, and they are the values that we are using. Procedure G, or step number G, we are having the results recorded in a suitable table, including values of T squared and L in meters. I've included that column to ease my work, so take that into consideration. Procedure, you're having the next procedure, that is procedure H. Procedure H is telling us that a graph of T squared against L was plotted and the slope S was calculated. Lastly, procedure I, the value of acceleration due to gravity was calculated from G equals to 4 pi squared over S, where our S is the slope of the graph. Where is this coming from? This is theory. Theory work, go and check your notes. Where is it coming from that you're coming to conclude with this equation? And then we move on now to the experiment and how to carry it out, and we shall get the slope, we shall get the conclusion, and that will be the end of the experiment. So we are still continuing, and this is my stopwatch that I'm going to use. This is the pendulum with a thread tied on it, and then I'm having the meter rule. So as our procedures are saying, we shall begin with a length of 20 centimeters, meaning what I'm going to do, I'm going to come and measure 20 centimeters from this using the meter rule, 20 centimeters, and then up to there. So these are the 20 centimeters that I'm going to begin with. As you can see, my thing is going up to 20 centimeters, as you can look at it there. So there they are. So what I'm going to do, I'm going to tie them. I'm going to tie them from this point up to that point like that. Make sure that you have tied the 20 centimeters. You can still, you come to measure again. Yeah, it is 20. Those are 20 centimeters. And then I'm going to now I'm going to displace the pendulum through a small angle, and then I time for 20 oscillations. I'm going to use a stopwatch, which is here. First, I have to set it. You have to set it, and if I'm to set the stopwatch, I'm going to press this. I press that, then it is reading that, and then I press this other button to restart it. Sorry, This is the stopwatch that I'm having. Yeah, I press this other button to restart it, and I take it back to 0. After taking it back to 0, what do? I begin to displace this through a very small angle, and as I displace, I can pull it sideways like this, and then I leave it to oscillate. At the same time, I leave it to oscillate. Then I begin. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I've counted for 20 oscillations, and that's the value that I'm getting for the stopwatch. It is giving me 19.06. I recorded that value down, 19.06. Then after recording, I again measure a length of 30, this time at 30. I come back and measure my length at 30 centimeters. I can pull this. Then I measure up to 30. So I place my meter rule up to 30. We make sure the length is up to 30. So this one is at 31. I pull it back, and I can take at that point. After I measure that length at 30, come back. Let's recheck again. Yeah, there we shall go. So it is at 30 again, the pendulum bob. There it is. I'm again going to restart my stopwatch, and then I count for again 20 oscillations. I displace it and I leave it to oscillate. At first I don't count immediately, but I begin counting 20 oscillations when the oscillations have when they are at a stable state. So I can pull 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and it is giving me that value at 23 point. We shall take 23.09. Come on, okay, we are still moving on. I again come back and I measure this time. I'm going to measure how many? I'm going to measure 40 centimeters. Bring back your meter rule and place at this point up to 40 centimeters. Up to 40, that is it. And I measure up to 40 here. Sorry. You have to be so accurate that your length is 40. There it is. I will take that as my 40 centimeters. Then you just tie this over this, and then you continue. So my pendulum this time, it is at a length 40 centimeters. So what am I going to do again? I pick up my stopwatch, and then I displace once again. I displace at a small angle, and at a small angle, maybe some of us are not seeing the angle that I'm displacing to. I can pull it here like this, then so I release it. When you release it, begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. At 20, it is giving me 25.5. I recorded that. 25.5. 0.50. Maybe you are asking yourself, what is the S solution? When do I begin to count? I begin to count when my pendulum goes this side and comes back. It is you to choose which side is going to begin and then which side is it ending. I can begin to count when it is at this side, meaning it will come like this and go back. That is one oscillation. If I begin from this side, it will go and then come back. That is one oscillation. When it goes and comes back, those are two oscillations. So note that going like this and then those are two. No. Yeah, you may be confused which one is oscillation, and you are counting when it goes back like this, one, and then like this, two. No, that is not the case. Please, we count the oscillation when it goes and comes back. Okay, we are still continuing. This time we are going to 50 centimeters. 50 centimeters. And at 50 centimeters, I'm going to count at 50 centimeters. I place my meter rule up to 50. This length should be 50 centimeters. Yeah, and there it is. If you may look through, it is at 50 centimeters. This point here, like this, we count there. Then I tie this other end at 50. And then I reset my stopwatch at 00, and then I displace again at a small angle. When I displace, I may leave it to first go, then I choose when do I begin. So I'm going to begin. Okay, sorry, let me do it once again. Let me first leave it, and then it goes, comes back. So I can choose to begin either from the other side and it comes, and it is C. So if I can begin, I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. At 20, we are getting 28.25. Record that down, please. 28.25. Yeah, that was at 50. We are remaining with 60 and 70 as our, those are the values we chose. Then I come back and I measure. I measure again. Measure again. I release it, move downwards, up to 60. That's about that. And I put up to 60. And that is my 60. So I'll just press small. Come now, our pendulum is there. In this place, pick up my stopwatch and begin to count. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. At 20. So at a distance of 60 centimeters, it is giving us 30.56. We are remaining with the last one, that is at 70 centimeters. Come back. Come back and measure the distance here, up to 70. Up to 70 down here. Yeah, you see it? It's up to this point. This is the 70 here. Here. After that, we go to this place. Very small angle. Okay, are we there? Yeah. And I'm going to pull the rest of my angle, and then I leave to this place. I begin to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. At 20 oscillations, it is giving us 33.01. We are having our table. It is having 5 columns. The first column is for the independent in centimeters, then which we converted to meters. And when you convert it to meters, that's why you're having 0.200. But you realize why you're adding 100, because from centimeters to meters, it has 3 decimal places. Then the next column is the one for the time of oscillation, for 10 oscillations. And those are the values you obtain in seconds. The next one is for the period, also in seconds. The next one is for the period squared. So we squared the column for period to obtain the last column, which is a t squared. That is the table of results. And then we proceed on. So these are the values you are going to plot. You are going to plot a graph of t squared against L in meters. These have found my t, and those are the values. So after that, what am I going to do? I need to first get the scale, of course. If I first get the vertical scale will be equals to 2.776 minus 0.908, and then divide by 10. I'm getting my value, so it will be 2.76 minus 0.908 divided by 10. And I'm getting my value as 0.1868. Now, when you look at this value, it falls between 0.1 and 0.2, meaning our scale will be equated to 0.2. So we shall approximate to take our scale as 0.2. Why? Because this value is right between these two. Then How many does one small square represent? One small square represents 0.2 divided by 10, giving us 0.02. Likewise to horizontal scale. Horizontal scale. Now for horizontal scale, we can see we're having 0.2, 0.3, 0.4, 0.5, and up to 0.7, meaning literally we can just say, we can just take two, we can estimate from here and we say two big squares can take 0.1. If I begin from here, I will say 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, meaning that one, it can be catered for. There's no need to find it here. Maybe just to illustrate still that if 10 small squares represent 0.1, one small square represents 0.01. That is for horizontal. But the scale we are going to use, use 0.1. Why? Because its values are already in a particular scale they are falling in, and that is 0.1. So coming back to my graph, I first demarcate it. And demarcation, I mean, I can begin from this. I draw my axes up here. Up you'll be seeing them. My line is this. For the emphasis sake, I will mark it again. Then likewise this other line, I'll be marking from here, like that. Then at this end, I put my arrows, and likewise to this other end, I'll put my arrows. Please let not the arrows pass through, but rather they should be exactly on the value. What next? The next thing I'm going to do is to first put my title. Our title is going to be a graph of what? Of t squared against L. After that, I underline it very well. Underline it very well. You can choose to write in uppercase, that is capital letters, or in small letters as it is there. Then the next thing is to name or to label your axes. And I'm labeling, this one is t squared. Now take note, my title has no units and it has no words. This is representing the period, but I'm writing its symbol, t squared. Likewise, this one, length for L. So don't write length and don't write period. Don't write here in seconds squared and also here in brackets meters. No. The title has no units. Take note of that. Likewise, down here, I also come and note it. It will be having L in brackets meters. I begin putting on these values. On the horizontal, I'm going to put 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and then 0.7, and then 0.8. This is it. Like this. You go on marking it. Likewise, I come on this and mark it from here, from here, from here, and mark at this point, and mark at this point, mark at this point, I mark at this point, and mark that, and so on and so on. What next? Still, we've said on the horizontal you are going to use a scale of 0.2. So I will come, if I begin from, but first check your value, your least value in the column of t squared is 0.9. So if it means if I begin at 0, 0 here, you realize my 2.2, my 2.7 will be outside. What do? I reduce this value by the scale, meaning I'm going to say, for me to get the starting value to be equivalent to getting my list value minus my scale, which will be 0.908 minus 0.2, giving us 0.708. But of course, I'm not going to write 0.708. What am I going to write? I'm just going to write 0.7. I add on 0.9 plus 0.2, 0.9. That will be 1.1. So 1.1, 1.3, 1.5, 1.7. 1.9, and I'm having 2.1. I'm having 2.3, 2.5, and then 2.7, then lastly up there. So meaning lastly up to 2.9, which is at this point 2.9. So that is what I'm going to use, and this is my plotting area. I've labeled the axes very well with the correct labeling. What next? The next thing is for me to plot. Now, plotting, still on the x-axis, the values are already seen, 0.2, 0.3 up to 0.7. How about on the y-axis? The y-axis, the values are not all that visible enough because you're having 2.776. How am I going to plot it? What to do? We first do like this. We first put these values in, we convert them into squares. Meaning if I have 0.9, 0.8, 1.334, 1.626, 2.33, 2.77. I'm going to convert these values into small squares. By how am I going to do it? I first get, we've said up here, one small square is going to represent 0.2. Meaning I'm going to say that, meaning I'm going to get, what I'm going to do? I'm going to get this value, I'm going to plot, for instance, 0.908, 0.908 minus my beginning value, which is 0.7. I get 0.208. What are we doing? We are plotting the value. Plotting the value. And I'm saying we get our starting, the value to be plotted. In this case, it is 0.908 minus the starting value, which is 0.7. Divide by what one small square represents. One small square represents 0.2. When we do this, so I'm going to divide this value and divide by 0.02. I'm going to get 10.04 small squares. Do you see that? Yes. The next one, I'm going to have 1.334 minus 0.7 divided by 0.02. I'm having 30. We can round off to 32 small squares. These are small squares. Then 1.626 minus 0.7 divided by 0.02. I have 46.3 small squares. 1.997 minus 0.7 divided by 0.02. I have 60. We can round off to 65 small squares. 2.335 minus 0.7 divided by 0.02. We can round off to 80. You see that? We can round off to 82. Why? Why am I rounding off some of them? Because this other value is more than 5. If it is less than 5, we shall take it as it is. So then that's 2.776 minus 0.7 divided by 0.02. I get 100. We round off to 4, meaning 104 small squares. So these are the ones I'm going to plot against my So we are length. Going to plot, and I'm going to plot 0.2 against 10.4. But since our 10.4, this 4 is less than 5, we shall round off to plot on 10 small squares. Likewise, we shall have 46, then we shall have 32, 65, 82, and 104. So I'm going to plot 10, 32 like that. At 0.2, I'm having 0.2, I count 10 small squares. So I round off to this point. Then at 0.3, I count 32 small squares. So these are from here to here, they are 10. These are 20, 30. I count 32. So up to 32, it will be somewhere here. These are 32 small squares. Then at 0.4, how many are they? There are 46 of them. This is 30, 40. I count 46. They are here. And then what else? At 0.5, I'm having 65. So this is 40, and then 50, and then 60. I'll be counting up to here, 65. 65 will be at this point. And then at 0.6, how many are they? They are 82 small squares. I count, of course, from this side, 10, 20, 30, 40, 50, 60, 70, 80. And at that point, I'm counting 82. So 82 will be at this point here. Remaining with this at 0.7, that is 70 centimeters. And we said at 0.7, we are counting 104 small squares. So it will be at this point, from here going up to that point. If 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 100 is at that. Then I add on 4 small squares, and they'll be here like this. So we are almost done with our graph, and that is how it is. You see it? This is it, the whole of it. So what you're remaining with is getting the line of base fit, and then we move on to getting the slope and the conclusion, and the graph or the practical will be done. When it comes to getting the slope, we're having 6 points. We're going to place our roller in such a way that it leaves equal number of points on either sides. And I can't choose my ruler to go through any of the points here. If I choose for it to go through this point, so if I choose I can choose to go, there's this point, okay, so there's this point here, and I place it like this. You go on testing and see which one can really bring out what you want. Having this 1, 2, 3. So it is leaving. I'm having 1, 2, 3. So it is leaving one upwards and another downwards. But it is touching this last one. So I'm going to go there. I can plot my you can make it like this. And there it has gone through this point. It has gone through this point and this one, but it has left this side and this side. But it is at least touching this one, which is a fair slope. I demarcate. I still come this other side, and I choose this point where I'm going to. These other points at the end, you choose them depending on which one is the line going through. So it is not just for the sake, but it is which one is the line going through. So in this case, my line has gone through that point. There are as many as possible, but you choose one of them. And I draw my line downwards. I draw my line downwards and downwards like this. Then also I also come and do the same this other side. This other side, I can take this one here. This is the one which is through which the line is going through. I make this line bold, but then this other end I make it dotted. But even this one, it will be a dotted line. Are we there? Then also this other side, I'll make a dotted line. So what you are meaning with, this is a right angle triangle. What you are meaning with is for us to get these coordinates here, and even this one here, which are going to help us to obtain the slope. So this coordinate, I read this and I read this for here. Then this one, I read this and I read this. So x1, y1, x2, y2. Okay. So when it comes to this other down one, I'm having my x1, we are lucky that it is coinciding already at 0.2, so it will be just 0.2. And then, then how about this value here? This value, we can come back and calculate for it. If one small square is equivalent to 0.02, then how many small squares are here? We count them. But remember, our graph was beginning at 0.7, so what are you going to say? You're going to say 0.7 plus into brackets. How many small squares are here? They are up to 8. There are 8 small squares, so it will be plus 8 times what one small square represents, which is 0.02. The value you get there will be that. So I can say 0.7 plus into brackets 0.02 times 8. I'm getting 0.86, meaning this is 0.86. Okay, coming back to this, I'm having also this one down here. It is down here. It is at down here. If one small square, of course, on the horizontal is equivalent to 0.01, yes. How about at this point? At this point, still, we shall also have, we shall say 0.7. This value here, then plus these two, plus into brackets 2 small squares times what one small square represents 0.1, giving us 0.72. So at this point, I will say 0.72. Then I go on also to calculate for these ones. I'm having 8 small squares, so it will be 2.7 plus into brackets 8 small squares times what one small square represents on the horizontal. We said it represents this times 0.2. Pressing the calculator, 2.7 plus into brackets 0.02 times 8, and you're getting 2.86. So that will be our 86. So now you realize I haven't included anything on my graph. I haven't indicated the scale. I have not indicated what one small square represents, or or the vertical. In physics, we may not necessarily write our scale on a graph. Reason being, if an examiner is marking and he comes and checks at this, he checks from here 0.0 to 0.1, then 0.1 to 0.2. Automatically it tells him that the scale is 0.1, so there's no need for you to write it here. Likewise, if I get 0.7 to 0.1, or to 0.9, and then 1.1, automatically the examiner will get to know that my scale is 0.2. So there's no need to write the scale on the graph if it comes to physics. For other subjects, it may apply. Okay, so moving on to calculating the slope, this is what you're having, and you're going to use this formula, S equals to change in t squared divided by change in our length, which is the L. And from the values we've got on the graph, we've got what I would call my T2 is the 2.86, and then my T1 would be the 0.86. Then on the x-axis, we are using 0.72 and 0.2. So as we substitute in the formula, we shall end up substituting and get 2.86 minus 0.86, the whole of that divided by 0.72 minus 0.2. You'll get your answer as 3.8 seconds squared per meter. Now check very well why we are getting 3.8. Yes, on the calculator it is having a very big value, but following the rules of standard figures, we are dividing two standard figures against 3. That's why our answer is taking 2, which is the least number of standard figures for the slope. So you're ending up getting 3.8. And also the units, we are dividing seconds squared divided by meters, giving us second squared per meter. Okay, then from that, we move on to now calculate or to relate the slope to the subject of what you are looking for. And the subject what you're looking for, in this case, is the gravity, or the value of the acceleration due to gravity, which you are calling g. And as we looked in the procedures, this value is obtained from g equals to 4 pi squared over s. I said on that if you don't know where it is coming from, check the theory. That is coming from the theory work. Check out and see how does it come. Then, so when you substitute for our s, we shall end up getting 4 pi squared divided by 0.8, giving us 10.3 meters per second squared. Now check how the units are changing. If s was down, meaning if s was in s squared divided by meters, when we divide, this meter will move up and s will be down. That's why you're getting meters per second squared. And also, the number of significant figures on our value, you're getting 10.3. But check what we've divided. We've divided two significant figures, which is 3.8. That's why we are having our value as 10. So ending the value with 10 meters per second squared. And I trust we are on the right track, because at least our value is falling in a particular range. Okay. Then now we shall come to the sources of errors. Sources of errors, we are looking at non-uniform oscillations due to wind. And yeah, there was some part of wind which was blowing. And how did I mitigate it? By closing the windows or the doors. You can also look for another way. Besides that, there's also inaccurate measurement of the pendulum length. Yeah, as you checked in my video, you realize I measured 20, but perhaps it stretched and maybe it went up to 21. Yeah, such inaccuracies arise the errors in our value. So how did you mitigate it? By measuring length from point of suspension to the center of the bow. The third one, inconsistent timing of oscillations. Like I said on, I can fail when exactly to begin counting the oscillations. Also that accounts for an error. How do you mitigate it? By ignoring the first few oscillations. Check very well the video, that's what I was doing. And also the elliptical oscillations due to shaking of the retort stand. Perhaps the retort stand was shaking, yeah. So it makes the pendulum to go in an elliptical form, in form of an egg or an oval. So such oscillation is not considered a perfect one. Okay, then from that we now go to the conclusion. Now our conclusion, we are having a conclusion. We've gotten our value as 10 meters per second squared, and therefore the conclusion will be the value of acceleration due to gravity obtained was 10 meters per second squared, which was in the range of 8.5 meters per second squared and 11.5 meters per second squared. Thus the hypothesis was true. Then this settled the learners' confusion about the teacher who told them that all objects fall freely at that rate. Yeah, sure, I believe it settled things up, and they were comforted with that value. Okay, thanks very much for watching my video. Please don't forget to hit the subscription button, like, comment and share to encourage me to make more of these videos. They are so educative and I'm so focused to helping a learner who is struggling, or to reaching a virtual lab to your screen. So go on and do that, please. Don't forget to share. There may be someone who needs this information. May God bless you. If you would allow me to pray with you, please, it will be very good. Father, bless these people, that as they watch this video, they will feel your power, they will get the knowledge, Lord, to excel in whatever areas of their weakness, especially under this subject. Thank you because you've given them wisdom. In Jesus' name, I've prayed and lived.